Hey guys, welcome to the second video in the Stereochemistry set. So this one is going to be showing you guys with the model kits, the concept of chirality, right? So remember in the first video, we talked about how if you have a chiral compound and we take its mirror image, you will not be able to superpose them on each other, okay? And also if you had an achiral compound and we took its mirror image, you will be able to superpose them on each other. So I just wanted to show you guys how this works through the model kits. Now, I know that on tests, model kits can take time, right? So there are tricks to get around this, and we can do that by using determining R and S configuration, which I will show you in the next video as a quicker way to do this stuff, okay? But I just wanted to show you guys with the model kits so you get an idea of how this actually looks, in 3D, all right? And so I made this model right here. So first thing we should do is figure out if this is chiral, right? There are three requirements for something to be chiral. The first is to have 4 unique substituents. Well, we have a white, a red, a blue, and a green sphere, right, or atom, on that one carbon, so that satisfies the first rule of 4 unique substituents. Now, is it tetrahedral? Yep. And also, is it sp3 hybridized? Yeah, it is. And so this is a chiral compound. So by definition, if I take its mirror image, I should be able to superpose that I should not be able to superpose that on each other. All right. So let's see. I want to take the mirror image right here. Okay. You can see the red, green, blue, and white are all mirror images of each other, right? So imagine the mirror running down this way. So we have the mirror image. Now, let's see if I can overlap it. I'm going to take this and I'm going to kind of put it right on top. You can see here that the green and white overlaps, but the blue and the red do not. All right, so let's try to rotate this. Take this, spin it around once. All right, now we have the white and the blue overlapping, yet the red and the green do not. So that doesn't work. Let's try it again. Another rotation. All right, the red and white overlap. The blue and the green do not. And so you can see I can just keep on going, and I could even rotate this one, and you'll see that you'll never be able to overlap them on each other. All right? So that makes this original compound here chiral. Okay? So what about achiral compounds? So what I'm going to do is I'm going to just take this blue one, and I'm just going to replace it with a white. Okay? And so how does this work? So we have this compound here. Now, is it chiral or not? Well, does it have 4 unique substituents? Not in this case, right? We have 2 white atoms and then a green and a red. So only 3 unique substituents. It's tetrahedral and it's still sp3 hybridized, but because it broke the first rule, it's achiral. Okay? And so now let's take its mirror image. So you can see here, right, we have everything here is the mirror image of each other. Okay? And so by definition, I should be able to overlap these on each other. Okay? So I'm going to take this and I'm going to play around with it to be able to overlap it. Okay? So you can see that the green and the green overlap, the white overlap, but then the other white atom does not overlap with it. We're getting overlap with the red. So you're going to have to play around with this to try to get it to overlap. Okay? And you can move around the original one too. Okay? So what I can do is I can take this, flip this around, and now let's see. You can see that the green and the green overlap, the red and the red, and then the white overlap as well. It's kind of hard to get them to show it here, but we can overlap them. And so this means achiral. Okay? And so we can see that it's achiral strictly because of this overlapping feature to it. Now, I get it on tests unless you're using a model kit, which can take time, and since the molecules are more complex, it is going to be hard to do it with this method, and I do not recommend people use this method. I just wanted to show you guys how it looks in 3D. Now, I will show you in the next video, after I cover RNS configurations, how you can use how we can use RNS to determine if you can overlap the two molecules together, stuff like that. Because on tests, what they'll do is they can give you two molecules and they'll ask you the relationship. Are they enantiomers, diastereomers, or are they just the same? All right, and the molecules will be in slightly different configurations, and so it's going to be your job to figure that out. Now, the quick way of doing this is strictly just determining if it's going to be RNS, at least because there could be more than one RNS carbons, but all you do is look at all the chiral carbons, figure out if it's RNS, and if all the configurations are the same, then you know it's just going to be the same molecule. But again, we'll cover that in the next videos. All right, so I just wanted to show you guys how this looked in 3D. If something here did not make any sense, please feel free to email me or speak to a TA at the CLC. If you're watching this on YouTube, you can also comment your question. Chances are, if you have a question on something, others have it also. So please don't be afraid to comment on it. And yeah, I will see you guys in the next video.